Now that we've thought about the pressure underneath an ocean of air, let's get back to the pressure inside an ocean of water again that we started with. But this time there's a twist. I want to start out looking at a diagram that should look the same as 2 lectures ago. There's a volume of water, and I have arbitrarily singled out any kind of subvolume of water. Just let's put some dashed lines around it here. And we already figured out in an earlier lecture what the forces acting on this arbitrary volume of water are from all of the other water pressure of all of surrounding water. Remember, the water pressure always comes in exactly perpendicular force to the boundary of whatever surface containing whatever volume we're thinking of. So there's arrows all over this irregular volume, on the top of it, on the sides of it, and on the bottom of it. Are all these arrows equal in magnitude? Are they the same length? If this diagram is drawn correctly, they are not. Which arrows are slightly longer here? Yes, you've got it. The arrows on the bottom, because there is higher water pressure deeper down in the water. We already learned that. So you have a lot of arrows on the top that are smaller, then they're getting bigger on the bottom, especially down here. And so the net addition of all those different arrows, it looks like it's not going to be pushing it sideways. The force cancels out, but the vertical force is up. It's called a buoyancy force, and we already know exactly what that force is. What exactly is that force? It's exactly enough force for hydrostatic equilibrium. It's exactly, I get a little tricky saying that, HSE. It's exactly enough force to balance the force of gravity, which wants to pull this weight of this fluid down. And of course, that is just the density of this fluid, which I guess here is water, times its volume, times G. That's mass times G. mg is the force down. No problems there. But now here's where it gets interesting. This buoyancy force could be acting on other objects that have different densities from water. So let's look at a more interesting case now. Just water holding up water is boring. Let's do water holding up something else. So here's an interesting material. Seems to be orange material, exactly the same shape. So it's taking up exactly the same volume as the water was before. I just instantly switched it here. This thing could be denser than water. Kind of looks like it is. But it has the same surface. And so all along the surface, what are the water pressure forces doing? You got it. Exactly the same as they were before. All these little F's haven't changed any from this previous diagram here. So, and we know there are smaller F's on top, bigger F's on the bottom where the water pressure is bigger. So what is still the same buoyancy force on the orange object? That's right. It's still the same as it was before. What was it before? It was the volume of the object times the density of water. In other words, it was the weight of the displaced water. Water is all gone now. I've got an orange rock or something in here. The water's out of there. It's displaced the water, and the buoyancy force is still the same. It's just enough to hold up an equal volume of water. Now, if this rock looks like is denser than water, that's not going to be enough buoyancy force to hold it up. The weight, if this thing is more dense than water, will exceed the buoyancy force. It's going to sink right down, accelerate down until it hits the bottom. But it is a substantial force, and so it's going to not fall down as fast with a strong acceleration as if it were just being dropped in a vacuum, for example. In other words, effectively, when you put an object in water or in any fluid, the pressure of the fluid helps you out. It wants to hold the object up a little bit, maybe not enough to hold it up completely if it's more dense than water, but it makes it effectively less heavy. It effectively offsets some fraction of the weight, which is very interesting and useful. So it effectively weighs less. If you put it on a scale down here in your swimming pool here, the scale would read that the weight of this object is quite a bit less than if you measured it in air or in a vacuum. Let's look at the numbers here. What I have just told you, by the way, is supposedly Archimedes' principle. I'm not sure that he was really the first person to figure out the buoyancy concept, but he seems to be the most famous and flamboyant person, so we all call this Archimedes' principle. Let's calculate it here using our formulas from 2 lectures ago. We'll just do a simple volume here, which is a cylinder, so it has a certain height. Well, the height, of course, is the difference between the top and the bottom depths. And then it has a certain cross-sectional area A. It's a cylinder, so A is the same at the top and the bottom. And all we need to know in this simple computation is, what is the water force of pressure pushing down on the top surface? And then what is the deeper water, under more pressure, pushing up on the bottom surface? I can neglect all the sideways forces around the side. They're all going to cancel out because it's a nice round cylinder. I only have to care about how much smaller this top force is than the bottom force, and that's very simple to calculate. Remember our formula, pressure, rho g times the depth. All right, so there's the pressure at the, let's do work on the force pushing up, because we know that's going to be larger. We know this is going to be a net force up. The buoyancy force will push this cylinder up. How much by? Well, at the bottom we have rho g h2. That's the pressure at the bottom. So we multiply that times A, and that's your force up on the bottom. The force on the top is opposing. That's water pressure actually pushing down. So we have to put a minus on, but it's only rho g a h1 because the pressure there is only rho g h1. And so you can see, since h2 is bigger, the buoyancy force is proportional to the difference in heights here. And for this particular cylinder geometry, which is a very easy one to calculate, I notice that that's the height of the cylinder, delta H, that's A, the cross-sectional area of it, so there's your volume of your cylinder. So the buoyancy force is rho, that's the density, we got to get this straight, that's the density of the fluid, because it's the water that's doing the pushing. I don't care about that beige block. I care about the density of the water that's doing the pushing. That's buoying it up. So we have the volume times the density of the fluid times G. What is the volume times the density of fluid? It's a sort of a hypothetical mass of how much fluid would have been there if we just took the object out. This is the MF, is the mass of the water, the fluid that was displaced. And that is the buoyancy force. So to sum up Archimedes' principle in one very simple sentence here, for a cylinder at least, the buoyancy force of any object when it's immersed in a fluid is equal to the weight of the fluid displaced. Now, that was a very simple proof that I just gave you for a cylinder, but it also works for any kind of complicated object with any shape. Even, I don't know, a Greek bust that's discovered somewhere in the Aegean Sea. This could be useful. Try to make it useful here. Suppose that you're looking at a bust which has a mass of 70 kilograms, and you're thinking, I don't know if our ropes are strong enough to pull that up from the bottom of the sea here and go take it to the museum. No, I'm sorry, we're going to sell it on the black market. Just kidding. This could be worth a lot of money here as long as we don't drop it. Good. All right. In our particular case, I guess this is made of marble. Anyway, it's 70 kilograms in mass. The volume is a good bit less than 70,000 centimeters because this is made of marble. It's made of something that's, I don't know, about 2.5 times denser than water. All right. Or suppose I just use my hands actually and go down there and see how powerful I am to lift it up. How much is it going to weigh? In other words, how much lifting force am I going to need? Well, there's a simple vector here before. I have two forces that I have to contend with. First is the downward force of the gravity on the bust, and of course that's 70 kilograms times G. mg here is 700 newtons. That's how much gravity's pulling down on it, and if there were no other forces involved, that would be a lot of force. That would take a lot of strength. But I don't have to exert all that strength. Why? Because I'm getting helped out by the fact this is surrounded by water. See all the blue there? It's water. The water pressure at the bottom of Archimedes' base being stronger than the water pressure here. A net buoyancy force of how much? How much is it? It's the displaced amount of water. Well, how much water was displaced? It says right here. 30,000 cubic centimeters of water was displaced. Well, we know the density of water. It's 1 gram per cubic centimeter. So that means that 30,000 grams of water, or 30 kilograms of water, was displaced. Would be here if we took the bust away. That's how much the volume would weigh if it were in water. So what is the weight of 30 kilograms of water? You know what it is. It's mg. It's 300 newtons. Pretty good here. So now that's already helping me out for free as long as it's in the water. I only have to lift up with a net force of 400 newtons. A little bit more. If I keep it 401 newtons, I can begin to accelerate this thing up to the surface. Hooray, I'm doing great, I'm doing great. People do this all the time, by the way, and what do they not take into account here? It's coming up, it's coming up, it's coming up. Just barely got it. Until what happens? You start lifting the head of the statue out of the water, trying to get into the boat. The more you lift the statue out of the water, the less buoyancy there is. Then you're only displacing less and less water. So this 300 newtons starts going down pretty fast. And by the time you're just about to lift it into your boat, you realize, oh crap, there's 700 newtons! Bam! And your rope breaks, and you have to give up. That has happened so many times I can't even tell you. It seemed like it was so easy when you're lifting it up in the water. You don't realize that the buoyancy force is going to go away as soon as it comes out of the water. Hope you won't make that mistake. More serious mistake here. This is the original historical, at least this is the story. This is how it goes. Archimedes and other people were, of course, always trying to help the authorities. And what was more important to the authorities than making sure that the crowns that they were given by whatever jewelers or goldsmiths to wear had to be made of 100% pure gold. Otherwise, I guess it wouldn't be a king. And how did they know that? It's very difficult. I mean, if the crown was very simple, if it was just like a cylinder, which was a block, and you could figure out how many cubic centimeters it was, then you could just weigh it on a scale and see if it was 19 times the density of water. It's solid gold. But of course they don't make, these clever goldsmiths don't make crowns like that. It has all these little crenellations and little features and bumps and things in it. Very hard to just look at that thing or measure it and try to figure out how many cc's of crown material is here, which we hope is solid gold. Forget about those little rhinestones that are set into it. We're mostly talking about just the crown here. We need a way to basically measure the density of that crown, or it's sort of putting another way, we kind of want to see what the volume of that crown is. And Archimedes, or the Archimedes principle, realizes that we could figure out what the volume of the crown is if we saw what the weight of the water it displaces when it's dunked in a tank is. Well, I hope it doesn't dissolve in water. That would be obviously a fake crown there. So yes, the king would let you, apparently he was buddies with Archimedes, so the king said, all right, you can, just to make sure that I'm not getting ripped off here, you can lower the crown into a vat of water here. See how much the buoyancy force makes it lighter than when I was measuring it just in the air. I'm neglecting the density of the air here. It's pretty small compared to water. Well, let's see. When the crown, we've got a 14.7 kilogram crown. Frankly, that's pretty heavy. If you had to walk around wearing that all day long, you'd probably get tired. Such a pain being the king, I'm sure. When you and you can't do this, if the king went into the swimming pool and dived down, then he would notice, or the measurement showed, it's only 13.4 kilograms times g. In other words, it's only 134 newtons. So it went from 147 newtons in the air down to 134 newtons in the bathtub, or in the swimming pool. What's the density then? Well, you can kind of see how this is working here. The crown itself must have displaced how much mass of water? The crown itself was displacing 1.3 kilograms of water. Well, what's the density then of the crown? 1.3 kilograms of water compared to 14.7 kilograms of crown means that the density of the crown compared to water is 14.7 divided by 1.3, which is about 11. 11 and a bit. Aha! Eureka! Archimedes is supposedly said when he realized this, and you know how the story goes, he's maybe not the first scientist to have had a eureka moment where he lost all thought of anything else where he was. I guess he was in the public baths, runs out in the streets to tell everybody his great discovery without noticing that he hadn't bothered to put on any clothes, thereby starting a stereotype about scientists which continued for thousands of years up to this day, that they have no idea what's going on. They're just obsessed about finding out the truth. And of course, I'm sure all of us have had little eureka moments, but that does not mean that we run around naked necessarily, unless we've really been drinking a lot more than they usually would in those Greek baths there where Archimedes hung out, unless it was an unusual kind of a bath. What was the eureka? Was this crown in this example made of gold? Interestingly, I'll tell you a hint here. If you have an object of lead, which just has a little thin veneer, a little polish of gold on the outside, gold filigree on it, that would be a density of a little more than 11 times the density of water. Density of gold, gold is dense, darn. Gold is 19 times as dense as water. This crown here is probably entirely made of lead except for a very thin layer of gold on the surface. Oh, kings don't like to be ripped off. Well, nobody does. And so here's where the goldsmith, the so-called goldsmiths, the leadsmiths are. That's where they ended up. It's thanks to, and he's pointing at, Archimedes, you are such a jerk. Wish you'd stayed in the bath there and let me make some money. Now, this whole principle, I don't know if Archimedes realized this, also works for objects that are floating in water that are much less dense than the water. See if I can scroll up a little here. So, contrasting the case where we have a very dense crown that just gets a little bit less heavy, a little less weighty in the water, what if you displaced a large amount of water with an object that was less dense than water? People don't realize this, but wood is less dense than water. I don't know, it's got air pockets or something in it. Not quite sure exactly what the biology of that is. Probably you guys can explain it to me. But I'm going to give you a not totally unrealistic case here of a log of wood, which is definitely less dense than water. It has a volume of 2 cubic meters. So if it were like, I don't know, ice or water or something that was close to a density of 1,000 kilograms per cubic meter, then it would have a mass of 2,000 kilograms. But this log, we're told in this problem here, I'd like to give a few examples. Look, I don't know if it's perfectly realistic or not. Anyway, we got a log in here. It's a very light log. Maybe it's made of balsa wood. I'm sorry, I don't know exactly. But anyway, it only has a mass of 1,200 kilograms. So how much does it weigh in the water, according to the principle of buoyancy we just talked about? Well, actually, technically, it weighs less than 0 in the water. What I mean by that? The buoyancy force on this thing is larger than the actual gravitational force going down. The gravitational force going down is only 1,200 kilos times g. It's only 12,000 newtons. But how much weight of water was displaced? Well, 2,000 kilograms of water was displaced, so that's 20,000 newtons of buoyancy force. So we've got a net buoyancy force going up here of, it looks like, I don't know, 8,000 newtons. Wow. So that thing, if you submerge it underwater all the way, it's going to take force to push it down. And if you let go, it's going to come up. It's going to accelerate up pretty fast. There's a net acceleration. It's going to pop up onto the surface, bounce around a little bit until it settles down into an equilibrium where all the forces are balanced. And where are the forces going to be balanced? Forces will be balanced when the buoyancy force is exactly equal to the weight of the log, mg. Well, the weight of the log is 1,200 times g, so the buoyancy force has to be 1,200 times g. In other words, the log will settle down, and this drawing is not quite perfect, the log will settle down here until the condition for it to settle down in equilibrium is it must displace that amount of weight of water. It must displace 1,200 kilograms of water. In other words, it must displace about 1.2 cubic meters of water. You got it. Because this log is 60% the density of water, it's going to ride with about 60% of its log mass in the water, if this is a uniform log. 40% of the log will be sticking up. Doesn't need any more buoyancy than that. If you push the log down and displace more water, it'll pop back up. If you lift the log up a little bit more, oops, not enough buoyancy, it'll sink back down. This is the equilibrium it wants to settle down into. That could be useful, and I have thought about this quite a bit. You could, for example, load some more weight on here. Yes. For example, suppose you're in a pinch. You need a raft. Wonder where that could come up. Well, this raft right here, this log, still has potentially what? Another 800 kilograms, whoa, of weight that you could load onto it. If you put 800 kilograms of something up here, such as a person, such as two persons who were in love, then the log would still just barely be sticking down all the way into the water, and the people would be just a little bit above the water level, and they could survive without having to get wet. Wouldn't that be interesting? Do you see where I'm going with this? I've been thinking about this problem a lot. I've been thinking about this problem at least since the second midterm exam in Physics 6C a few years ago. It's exactly the same problem. Let's set up the actual, historical facts that this problem was based on. In case you haven't seen it, I feel you should see it again here. Jack and Rose, they've survived the sinking of the Titanic. Now they're floating around in a field of a bunch of debris and junk from the wreckage of the Titanic, and they're trying to survive here. Everybody's trying to survive. They got to get out of the water. That water is pretty close to freezing. You can't survive for more than a matter of minutes in that water. But if you can get your body out of the water, you have a chance of surviving when somebody will eventually come along and save you. So what happens here? They're the only two people who notice that one of these huge, heavy wooden doors is floating around there. Looks like it's obviously floating because it has a lower density than water, ought to be able to support the weight of some people on it, keeping them out of the killing, freezing water. So let's see what happens. In French, no less.
Stay on, Rose.
Uh-oh. Only Rose got on. Jack, you're still in the water. You're freezing to death. Look, she's barely out of the water. He's nodding. Oh, brother, his door is just not big enough. And this guy doesn't believe it.
It's just enough for this lady. We'll push it under. Let me try at least, or I'll die soon.
That's what I was thinking.
We'll die sooner if you come any closer. Yes. Nice. Good luck to you then.
Wow, that guy was very agreeable, wasn't he? That's really the climax of the movie right there. Jack and Rose see a way, which according to him, is a way that only one of those two people can survive. The other guy over there is like me. I was looking at this quite a bit in the movie. It turned out that I went to that movie on a date with someone who ended up eventually being my wife, and she was all weepy and romantic about it. I'm going, come on! That door looked huge. Why couldn't they both get on and survive? And that's what this problem wants to calculate here. Jack and Rose swim up to a wooden slab. It's a door. They recognize it has a density of only 650 kilograms per cubic meter, only 2/3 of the density of water. That can be used for flotation. There should be extra buoyancy force that could hold their bodies up. It is 3 meters wide and 2 meters long. I approximated that by looking. It was a big door in the movie. Let's say it was 9 centimeters thick. So how much volume is that? We do a quick calculation here in cubic meters. We're going to do this in cubic meters units. It was almost a little more than half a cubic meter. So if that door has to go all the way down and just barely keep Rose and her delicate body out of the water, then we can displace this much mass of water. The buoyancy force then is going to be 0.54 cubic meters. So I calculated it here, if you're wondering, and it comes out, according to me, O times G is 10. So let's see, we have 10,000 times 0.54. It comes out to 1,890 newtons. I'm going through this pretty quickly. Well, how much does Rose weigh? Some people criticize me on this. Look, I just have to make an estimate of this. You know, she was sitting around on the ship for a while, eating a lot of first-class food. I estimated 65 kilos. There is a scene where they do a drawing of her, and I don't know. That was just a guess anyway. I'm guessing for simplicity in this problem, she weighs the same as Jack. Well, if they weigh the same, then the total force that both of them would exert on that door would be 1,300 newtons. And frankly, the movie would have had a very different conclusion if my calculation here turned out to be right. In general, the fraction of the object, if it's a uniform object of a density less than water, like I showed before, the fraction of the object that's going to ride above the water line will be 1 minus how much less dense it is than the density of the water. In other words, the amount of volume that it actually displaces compared to its total volume will be the ratio of the density of the object compared to the density of water. So for wood here, I was taking this to be about 2/3. So with no weight put on top of it, nobody riding on top of it, Rose, then you would have about 1/3 of the wood sticking out and 2/3 of it providing the buoyancy force displacing the water to hold it up in hydrostatic equilibrium. Let's see if you really understand this now. Quick conceptual example here. I've got your 2 pails of water here. They're identical pails, the same size. In both cases, the water's filled to the brim. But in one case, it's just a pail, just water. In the other case, though, I started out that way with a pail with water, and I take a block of wood or something that's less dense than water, something that floats, like a little wooden ship, whatever the heck it is, something, a canoe, paddle, whatever. Put it in there and let it float on the surface of the bucket of water, which will obviously displace some water. So some of the water that was in my second bucket here has been displaced and dribbles down and goes away. Which of those 2 pails, the original pail that's just full of solid water, or the new pail which has some piece of wood floating in it, so it's added the wood, but it's displaced a certain amount of water, which pail weighs more? You take the pail, the one with the water, the one with the wood, you stick it on a scale. Maybe I'm going to do this in class just to see if it comes out that way. Which one weighs more? Trick question, isn't it? It's all about that water that got displaced when I stuck the wood block in. Well, how much water was displaced when I stuck the wood block in there? Remember, the wood block is floating out of the water, so it only displaced its own weight in water. It's not sunk to the bottom there, it's just floating there with a little bit of it some of it in the water, some of it out the water. So the wood block exactly added the same amount of weight that was lost from the water slopping over. The 2 pails should be exactly identically equal in weight. One of them has more water, the other one has a little less water plus a piece of wood. Adds up to the same weight. Let's do a second scenario, or see if this second scenario is different or it's not different. Suppose it wasn't wood, suppose it was something that was denser than water, so it sinks to the bottom, like rocks. I drop some rocks in the bottom of the bucket. They sink to the bottom of the bucket, they displace some water. Which one's heavier now? You got it? Of course, in this case, it's different from the first case. They will no longer be the same weight because the rocks could not displace enough water to equal their weight. They have more weight. That's why they're sinking at the bottom there. In fact, if you keep filling that bucket with rocks, it's just going to get heavier and heavier, even if there's no water left in it. So obviously, in the case 2, if the objects are sunk to the bottom instead of floating, then that's making the total amount of bucket plus rocks plus water heavier than it started out when it was just water. All right? Now, one more fun illustration. Nope, there's got 2 more fun illustrations here. How do you measure fairly precise differences in the density of a fluid? This is a classic problem, for example, when you're brewing or trying to make wine, trying to make some alcohol and so on. Alcohol being a little bit less dense, the way you tell how far things have gone is you must precisely measure the density in the vat here. And so you take a hydrometer. It's designed specifically for this purpose. It's a long tube with a vacuum in here, or pretty much, except that there's a weight at the bottom. Now, I'll try to give you a fairly realistic example of how this hydrometer works, so we're going to put some actual numbers in here. Let's see if we can do that. The tube is going to have a 2 square centimeter cross-section. Cylinder probably work good, and the total tube is 25 centimeters high. So what's the volume of this tube? The total volume would be 2 times 25. The total volume would be 50 cubic centimeters. I'm going to do this in cubic centimeters because it seems a little easier in this problem. You could convert it all back into meters and kilograms, and then you'd still get the correct answer. Now, we are told that the entire weight of this hydrometer, the glass plus whatever the weight down here in the bottom is, the whole thing adds up to a total mass of 45 grams. So the total average density of the hydrometer, it's like one solid piece here, is a bit less than water. It's only 45 grams divided by 50 cc's. It's 90% of the density of water, a specific gravity of 90%, 0.9. So according to what we just looked at from Archimedes' principle of buoyancy, if you put this thing into water, which would have a density of exactly 1.000 grams per cubic centimeter, then we already know that because this is the density of the hydrometer, average, it's 90% of the density of the water that's supporting it with buoyancy force. 90% of it is going to submerge. So it has to sink down a depth of 22.5 centimeters. That's 90% of the way down. So all you have to do to make very precise measurements of density is to put a little line right there at 90% down. And then you can put other lines here. Which way is it going to go? If this fluid now has a lot of alcohol and it's getting less dense, then if it's less dense, then what's going to happen? The hydrometer is going to sink down lower because it has to displace more fluid. It has to displace 45 grams worth of fluid. And so somewhere up here will be a mark for 99% density of water, 0.98 specific gravity, 0.97, 0.96. Of course, if you stick it in something, I don't know, some fluid which is more dense than water, like, for example, salt water. It's very salty. That's actually denser than water. Then it'll ride higher. So this would be like 1.01, 1.02, and so on. And so you can make very precise measurements of the density of a liquid. And this thing is designed, the way I got it here, that it makes quite accurate densities measurements around a density of 1 times the density of water. One final example, which I think is a very important example. It's going to be on the exam. That's how important it is. This whole buoyancy idea that Archimedes came up with and is famous for also applies when you're in an ocean of a fluid such as air. Air has some density to it also. It's about 1,000th the density of water, but under certain circumstances with a large quantity of air, you don't want to forget that. Because if you were to displace a large volume of air, then there should also be a net buoyancy force up. If you displace it with something which is, you got it, less dense than air, it's called a balloon or a lighter than air ship. Let's look at an example here. Let's take a volume is shown by the blue here. It's in some kind of rubber balloon, and we'll fill it with helium. Why did I pick helium? Because helium is definitely less dense than air, right? Why is that? Because air is mostly molecules of nitrogen, and nitrogen, let's see, has 7 protons and 7 neutrons, and nitrogen is a binary diatomic molecule, so every molecule in nitrogen has 14 plus 14 stuck together. It has 28 atomic mass units. What's the atomic mass of a single helium? 2 protons, 2 neutrons, it's just 4. 4 versus 28. Helium is only 1/7 the density of air, so that sounds like a very good start then. So, if we get a balloon that has helium, what's the buoyancy force on it? Well, the buoyancy force is the weight of the air that was displaced by this balloon. In other words, it's the weight of air of an equivalent spherical volume here, which is not nothing if you have a big balloon. And so if the and of course there's still gravity on the helium, but it's not very much, because helium is so much less dense than air here. So of course we could actually add a load like a basket here. Hey, just occurs to me, this would be a completely different ending for that movie. Rose and Jack, if they had enough helium there, they could have made a balloon, and if it was big enough, they could have put a little basket on it, and it could have lifted them to safety. That'd be an interesting movie. Maybe that's for Titanic too. But, or Lusitania or something. I don't know. You can see everybody's an amateur filmmaker around here. We should leave this to the professionals. But anyway, let's leave physics to the physicists here. And so the buoyancy force could be enough to lift up both the mass of the helium, m helium times g, which is small, plus, in this particular example, we've got to figure out, see, I always give you 2 of the quantities, you figure out the 3rd quantity. Here, I'm telling you what is just the maximum load. Interesting. It reminds me of the weight of Rose and Jack. I don't know why, plus a little basket for them to sit in, and a little cushion for Rose's pretty head. Anyway, the mass that has to be lifted by this buoyancy force is 180 kilograms, or 1,800 newtons here. And so this tells you about how big the balloon has to be. It has to be big enough to at least displace 180 kilograms of air, and then some. Actually, for the helium. Well, air is about 1,000th the density of water. It's about 1.2 kilograms per cubic meter. So if I were to neglect the weight of the helium, I would need a 150 cubic meter balloon. That's a pretty big balloon, actually. They probably didn't have those in the steerage class on the Titanic. You have to be a rich person to bring along your own balloon of that size. Well, in fact, the actual answer is it's going to be a little bit more than that, maybe 160 cubic meters or more, because you also have to have enough buoyancy force to lift up the helium. Helium has a bit of mass also. Wonder if you could make an even more efficient balloon. Maybe I could get by with something that's smaller. Like, could I get by with a balloon that's closer to 150 cubic meters? Yes, I could. I could find the one gas which is only half the density of helium. So it would be half the weight of helium. You could add a little more passenger weight in it. What would that be? The diatomic gas H2, hydrogens. 2 hydrogens stuck together. That has only half of the density of helium. And so that gives you even a little bit more lift than helium. Ta-da! As was done in the famous another great disaster. This disaster was so short that it made a very boring movie with George C. Scott. The Hindenburg! Yes. Now, of course, after the Hindenburg blew up and totally incinerated everybody because some static electricity built up and it caused a spark that wasn't anticipated and so on. It was really very bad luck, actually. They found out that helium is very flammable, at least for a few seconds anyway. And nobody ever tried to build a lighter than airship, a dirigible or something that's hundreds of feet across there to carry all those people. In great comfort, by the way. Very smooth ride. Nobody ever tried it again, and I think that's really a shame, and we just don't really have that much helium around to really do this a lot anymore. So that's a really missed opportunity there. But you know something that this is showing here, it's interesting, we're always in this sea of air. So there's always a little bit of a buoyancy force on me. So for example, when I got on the scale this morning and I looked at how much I was weighing down, I was not actually exactly measuring mg, my mass times g. I would forget the clothes and everything. Oh, it was Archimedes. I didn't have any clothes. Anyway, never mind about that. Just got out of the shower. I was measuring mg minus the buoyancy force of the air that I had displaced. But the air that I had displaced, was, like I said, I'm density of water pretty much. So the air I had displaced was only 1,000th of the density of me, so that scale reading only underestimated my weight by about 1 part in 1,000. Okay, so it's still too large a number, let's face it there. Even anyway, 1,000th isn't going to make much difference. That is such a small effect that people always just completely ignore that. If you want to measure very precise weights and so on, you ought to measure everything in a vacuum. I prefer not to do that when I'm weighing myself, but if you want to do precise measurements, get all the air out to eliminate the buoyancy force. Now you know.